Hello there. So today I'm going to talk about a problem that involves the application of heat conduction equation for steady state conditions. So let's read the question first and then solve the problem. A bimetallic disk is created by fusing two disks, one with radius A, thickness D1 and thermal conductivity K1, to a second disk with the same radius. So that means the two disks will have the same cross-sectional area because their radii is the same. But the second disk will have a different thickness D2 and a different thermal conductivity K2 purely because it's made out of a different material. You can see a diagram of this bimetallic disk. At steady state conditions, so this is very important, we are looking at steady state conditions, the outer flat surface of disk 1, that is this part, is maintained at a constant temperature T1, and the outer flat surface of disk 2 is maintained at a constant temperature T2. You can see T1 is greater than T2, so the heat will flow from T1 side to T2 side, that means from left to right. Now, since we are looking at steady state conditions, inside the bimetallic disk, at any point, the temperature does not change. The temperature is a constant. So as a result, I can consider that at the boundary of disk 1 and disk 2, the temperature is Tm and that is also constant. So now I'm going to apply the equation that we are going to use to solve this problem is the heat conduction equation for steady state cases. So for steady state cases, for steady state situations, the heat conduction equation can be written as, let's say the rate of heat flow, let me call that R prime, equals heat divided by time, this lowercase t is for time, equals the thermal conductivity times the cross-sectional area times the temperature gradient. So that means a change in temperature delta T divided by the length, the change in length or the thickness in this case, delta L. This uppercase T stands for temperature. So this is what we call the heat conduction equation for steady state cases. Okay, so we are going to use this equation twice, once for the disk 1 and the other time for disk 2, and then combine the two equations using this interface temperature Tm. So let me first write down the heat conduction equation for steady state for disk number 1. So then I have R prime equals K1A. The temperature gradient would be T1 minus Tm divided by the thickness, which is D1. Now for disk 2, I'm going to write down the same equation. This time the rate of heat flow would be the same. It is steady state. So the heat going into the system is the same as the heat flowing out of this bimetallic disk. So I have R prime equals K2 because disk 2 is made out of a different material. The cross section is the same because the radius is the same. Now comes the temperature gradient. This time it would be Tm minus T2 divided by that thickness, which would be D2. Now both sides, you can see both equations, the left hand side is the same. So I'm going to equate the right hand sides of these two equations. Let me call this equation number 1, and this equation number 2 for simplicity. So from 1 and 2 I'll have K1A T1 minus Tm, and I'll divide K1A by D1 and I'll put parentheses like that. So then it becomes more clear what I'm doing. Similarly, on the right hand side, I'll have K2 times A divided by D2, and within parentheses I'll have Tm minus T2. Okay. Now what I'll do is that I'll simplify, I'll cross multiply this side. So my right hand side would become K1 D2 K1 D2 divided by I have K2 D1, and you can see in the numerator and in the denominator I'll have A and A. Those two will cancel out. Okay. And then I have on the left hand side I'll have T1 minus Tm, and on the right hand side Tm minus T2. Now this part, for easiness of simplifying the algebra, let me call this as x. Later on we'll substitute back this expression for x, but for now let's use x so that it becomes much more simpler solving this problem. So as a result, the equation becomes x times t1 minus tm equals Tm minus T2, and then I can distribute the x. I'll have x T1 minus x Tm equals Tm minus T2. Now I'll solve for Tm. So when I solve for Tm, I'll have 1 plus x, and on the other side I'm going to have x T1 plus T2. Okay. Now I'll solve for Tm, which would be x T1 plus T2 divided by x plus 1. So this is my expression for Tm. Then I can substitute Tm, this expression, for either equation 1 or equation 2, and then solve for the required expression in the problem. So I'll use equation number 1. Okay, so then I have r prime equals k1a. I'll divide k1a by d1, and then I have t1 minus, for tm I'll substitute this expression. So I have x T1 plus T2 divided by x plus 1. And then I'm going to use a common denominator and simplify this expression within the square brackets. Furthermore, I'll have r prime equals k1a divided by d1, and then I'll have x T1 plus T1 minus x T1 minus T2, and the common denominator x plus 1. Now you can see x T1 cancels out with minus x T1, so it becomes much more simpler. The expression becomes more simpler. So then I'll have the rate of heat flow as r prime. This is using equation 1. K1 A divided by D1, and within the square brackets I'll have, what do I have there? I have x plus 1 in the denominator, x plus 1 in the denominator, and in the numerator I have T1 minus T2. Now x is something that we defined, so we need to substitute back for x, which is k1 d2 over k2 d1. So k1 d2 over k2 d1, that is x. So let's substitute that back into this equation. So I have r prime equals k1a divided by d1, and T1 minus T2 in the numerator divided by, for x I'll substitute K1 D2 divided by K2 D1 plus 1. Okay. Now the question is asking for the rate of heat flow per unit area, and that is defined as R. So R in this case would be the rate of heat flow divided by the cross-sectional area A, because we are looking at a unit for a unit area, the heat flow for a unit area. So that's why I need to divide R prime by A, and then that's equal to the heat flow per unit area perpendicular to the cross section of the bimetallic disc. So in this case, I'll have, as a result, I'll have K1 D1, and then I'm going to solve the denominator. I'll have K1 D2 plus K2 D1, and in the numerator I'll have this denominator part, one of the parts, that would be K2 D1 times T1 minus T2. Now you can see this D1 in the numerator cancels with the D1 in the denominator, and then I have this expression K1, K2, T1 minus T2 divided by K1 D2 plus K2 D1. So that is my R. This is my R, the rate of heat flow per unit area. Now what I'll do is that I'm going to divide the entire numerator by K1 and K2 and the entire denominator by K1 and K2, and then I should get the required expression. Okay, so this is what I'm going to do. I'm going to divide the numerator by K1, K2 like this. So that's not a plus sign, that's basically a minus sign, so I need to write that again. So I have T1 minus T2. I'm going to divide the entire numerator by K1 K2 like that, and then the entire denominator, which is K1 D2 plus, this is a plus sign, K2 D1, and that part I'm going to again divide by K1 K2, and then we should have our expression. Okay, R is equal to the numerator, you can see it's T1 minus T2 divided by the denominator becomes D2 divided by K2 plus D1 divided by K1, and that is the expression that we are looking for, that the question is asking. This is that expression. So R stands for the rate of heat flow per unit area across the perpendicular cross section of the bimetallic disc. So this is how you solve the problem. I hope you learned something important about application of the heat conduction equation for steady state conditions, and the step-by-step method that I showed you will definitely help you to solve physics problems. So with that, I wrap up this session. Hope to catch you soon. Subscribe to my channel and like my channel, and if you have any comments, please comment below so that I can improve the content that I provide in this channel for your own benefit. Thank you very much.